Introduction. 1. What is RAM analysis? RAM stands for reliability, availability, and maintainability. It is a quantitative system-level analysis methodology used to measure how often a system fails. Reliability. Determine how much time it is operational and available for use. Availability. Assess how quickly it can be repaired and restored to service. Maintainability. RAM analysis is not just about looking at individual machines. It models the interactions between components in a system and how failures in one part impact the whole. It's a foundational tool in asset-intensive industries like oil and gas, power generation, manufacturing, and defense. 2. Why is RAM analysis important? In any operation that depends on physical assets, system availability is critical to productivity. Even a highly reliable machine can cause major losses if it takes too long to repair, or if its failure causes a cascade of stoppages downstream. RAM analysis helps organizations ensure capacity assurance, keep equipment running at its intended performance level, support risk-informed decisions, invest resources where they'll have the highest impact, prevent underperformance, identify system weak points before failure occurs, reduce downtime and cost, through smart planning of maintenance and inventory, improve safety and compliance by avoiding failure scenarios that pose risk to people or the environment. 3. Types of availability in RAM. RAM analysis categorizes availability into several distinct types, each offering a different level of insight. Inherent availability, AI, considers only corrective maintenance, excludes logistics, delays, etc. Formula, MTBF plus MTTR, best for benchmarking the intrinsic reliability of the design. Achieved availability, AA, includes both corrective and preventive maintenance, reflects more realistic operating conditions. Operational availability, AO, includes all downtime, repairs, waiting for spares, logistics delays, labor availability. Represents real-world availability, what the plant or site actually experiences. Most important from a business outcome perspective. Understanding these categories allows teams to pinpoint whether downtime is due to equipment issues, people, parts, or process delays. 4. Strategic application of RAM. The ultimate purpose of RAM analysis is to support smart, targeted decision-making. Which equipment should be upgraded for the greatest impact? Where should redundancy or spares be added? How can maintenance intervals be adjusted for better uptime and lower cost? RAM results guide leadership in capital planning, what to invest in, maintenance strategy selection, RCM, CBM, etc. Risk mitigation, preventing high-consequence failures. By focusing efforts on high-impact components, organizations avoid wasting time and money on low-risk areas, embodying the CMRP principle of doing the right work at the right time. CMRP modeling and simulation provide a way to represent and study how a real-world system behaves over time by using reliability, failure, and repair data. Instead of waiting for failures to happen in the field, simulations allow you to test scenarios virtually and identify weak points in the system before they cause downtime. This is especially useful in complex systems where many components interact, and failure in one area can affect the entire operation. Reliability block diagrams, RBDs, are one of the most common tools used in RAM modeling. They visually map how components are connected, whether in series, where the failure of one item brings down the system, or in parallel, where redundancy allows the system to continue operating even if one component fails. RBDs help clarify how individual assets contribute to overall system reliability. Monte Carlo simulations are often paired with RBDs to evaluate how the system performs under different operating conditions. These simulations use random sampling based on known failure and repair distributions to simulate thousands of potential outcomes. The result is a statistical prediction of performance metrics like availability, reliability, and downtime over a defined time horizon. Markov chains are another method used, especially for systems with clear operational states and transitions, such as standby, failure, or repair. They're useful for modeling simpler systems or systems where state changes follow a probabilistic pattern. Markov models can help predict the likelihood of the system being in a given state at any time, which is valuable for steady-state availability analysis. The key benefit of simulation is that it enables informed decision-making. By testing different configurations, maintenance strategies, or spare parts policies before implementing them in the real world, organizations can reduce risk, save cost, and improve system uptime. Simulation supports a data-driven approach to optimizing performance without interrupting operations. Sensitivity analysis examines how small changes in system inputs or decisions affect overall availability and performance. It's a way to test different what-if scenarios to understand which variables have the greatest influence on uptime. By doing this, organizations can focus their efforts and resources on the most impactful areas instead of making broad, unfocused changes. One key area of sensitivity analysis is redundancy policies. This involves testing whether adding standby units or designing components in parallel increases overall system availability. For example, having a backup pump that kicks in when the primary fails can drastically improve system reliability. Sensitivity analysis helps determine if the added cost of redundancy justifies the improvement in uptime. Maintenance strategies are another focus area. By comparing corrective, preventive, and predictive maintenance approaches, teams can evaluate which method results in the best performance for the least cost. Sensitivity analysis reveals whether increasing PM frequency actually improves availability, or whether predictive methods would be more efficient. Stock policies are also analyzed to understand how the availability of spare parts affects system downtime. If parts are frequently out of stock, repair times increase and availability drops. Sensitivity analysis helps identify optimal inventory levels to support uptime without overstocking. Logistics is often an overlooked but critical factor. Delays due to travel time for repair crews, slow supplier response, or lack of immediate access to tools and documentation can all extend downtime. Sensitivity analysis quantifies the impact of these logistical variables, showing how even minor process improvements can lead to measurable gains in system availability. Overall, sensitivity analysis enables data-backed decision-making by highlighting which operational levers, whether they're related to design, maintenance, inventory, or logistics, offer the greatest potential to improve system performance. Improvement allocation based on availability is about using data to decide where to focus reliability and maintenance improvement efforts for maximum impact. Instead of treating all equipment equally, this approach identifies the specific components that most directly affect the overall system's uptime. These components become the top priorities for investment, redesign, or enhanced maintenance. Two common importance measures help guide these decisions: reliability importance (RI) and availability importance (AI). RI measures how much improving a component's reliability would improve the system's reliability, while AI evaluates how a component's performance affects the system's availability. These metrics help identify bottlenecks in the system, the weakest links that limit overall performance. By using simulation results and importance rankings, teams can allocate resources like maintenance budget, spare parts, or redesign efforts, where they will deliver the greatest return. This prevents over-maintaining low-risk assets that contribute little to downtime and ensures that high-risk or high-impact assets are not neglected. This targeted improvement strategy supports smarter decision-making. It leads to higher uptime and system reliability with fewer resources, avoids waste, and directly supports business goals like cost efficiency, safety, and productivity. Instead of reacting to failures, the organization proactively invests in the areas that truly matter. Performance optimization is the process of fine-tuning system design, maintenance strategies, and resource allocation to achieve maximum reliability and availability at the lowest practical cost. Rather than simply aiming for the highest possible uptime, optimization seeks the best balance between performance, cost, and operational risk. This involves adjusting several key variables. System configurations can be changed, for example, by adding redundancy or rerouting workflows. Maintenance intervals can be shortened or extended based on actual asset performance and failure data. Spare parts strategies can be refined to ensure critical items are available without overstocking low-use items. Optimization is most effective when it's driven by simulation. Using modeling tools, teams can test thousands of possible combinations of maintenance policies, inventory levels, and design changes to see which one delivers the best results. These simulations account for real-world constraints like budget limits, labor availability, and safety requirements. Objective functions are used to guide this process. For example, a company might set an objective to minimize downtime, maximize availability, or reduce total maintenance cost. The optimization engine then searches for the best strategy to meet that goal within given constraints. The outcome is a maintenance strategy that is both efficient and effective. It avoids overmaintenance and unnecessary cost, while ensuring that reliability targets are still met. This approach supports continuous improvement by making reliability decisions based on performance data, not assumptions or guesswork.